And that brings us to a least squares regression line, which is kind of like the next step in a regression analysis. So if you've heard of a line of best fit, you've kind of heard of a least squares regression line. So a least squares regression line is a mathematically precise line of best fit. So in a test before, especially when you were younger, you might have been asked to draw like a line of best fit. You might have just like taken a ruler or even just your pencil and just drawn a line through it, like that estimated and roughly represented the overall trend. That's an awesome thing, but it's not mathematically precise. So the process of calculating a least squares regression line is how we get that to be more precise. And the formula of the structure of how we do that is y equals bx plus a, where y is our response variable, which we've discussed. B is the slope or the gradient. So this can be a little bit trickier to interpret. So the gradient, or B, estimates the average change in y, which is the response variable, for each 1 unit increase in the explanatory variable, which is x. And then A is the y-intercept, which is where the trend line or the line of best fit intercepts the y-axis. And the cool thing about that is that's always going to be when x is equal to 0. So that's kind of how you go about finding the y-intercept, because when x is equal to 0, so if, for example, I draw us a scatter plot example here, if, for example, our line of best fit looked like this, we can see that this here is where my line intercepts the y-axis. And that's really valuable to note because, well, first of all, because it's a part of our equation, but also because it tells us more about like our data. So we know that this point here is where it intersects. This is our this is our y-axis. So this is where our line intercepts our y-axis. Conveniently though, this is our x-axis, whatever our scale is. Might be 0, 1, 2, 3, 4, 5. Where the line intercepts the y-axis, it's always going to be when x is equal to 0. So that's another cool little trick as well, if you're ever needing to calculate that. And then coming back to like the slope and the gradient, so that estimates the average change in the response variable for each 1 unit increase in the explanatory variable, or like the x in the case of the formula. So here, for every 1 unit increase, we have in the x, which is again explanatory variable plotted along this axis, what's happening to our response variable. So in this one, we can see that with each 1 unit increase, our response variable is also increasing. So here you can see we're going to have a positive slope or gradient. It's going to slowly increase because for every increase we have in x, we also see an increase in y. Whereas, for example, if I had a negative line, for every increase in x, we're going to have a decrease in y. Increase, we're going to decrease, decrease, decrease. So it depends what type of like trend pattern relationship that we're looking at. But that is a quick overview of how to interpret the least squares regression line. So here you can see I've got an example. You can see that I've got y, so my response variable, which here is the price of the car. So here I'm saying the price of the car is equal to negative 0.0406 multiplied by the kilometers traveled plus 17,643. So you can see if my line was to continue up and intercept the y-axis, and you can also see x is equal to 0, the value that's going to be there is about 17,643. So that's using my line to predict what the price of a car is when x is equal to 0. So when it's traveled 0 kilometers, this line's predicting the price of a new car. But again, extrapolation isn't always super reliable for a lot of reasons, which we're going to touch on a little bit later. And then we can also see that for every 1 unit increase, so for every extra kilometer the car travels, the price of the car is dropping by about 4 cents. So that's how I'd interpret this here. Or that could be 0.04 cents. It depends on the unit we've used. Probably 4 cents, I think, if I am interpreting that correctly. But again, it's negative. So for every 1 unit increase, my response variable is dropping. So for every kilometer the car travels, it drops in value. The price of it drops, which makes sense because that's the kind of relationship that we're looking at. So again, calculating A and B by hand, bit of a time-consuming and painful process, but also really important. But you can also calculate this using your calculator. But again, it's not a substitute for knowing how to use the formulas in your formula sheet, because that's a really important part and could definitely be assessed on your exam as well. So similar process, mode 2 puts it into statistics mode. Then you press 2, which again is to get up that bivariate data table. You enter your values. Again, you press on. You press shift 1, 5. Again, same process as before to get into like regression, I believe. And then you can choose. 1 will give you the value for A, and 2 will give you the value for B. And then you can go back and do the process again if you want to find the other value. So you can also use your calculator to find A and B. Again, really helpful information to tuck away in the back of your mind. Another thing I'd love to touch on is the difference between like association and causation. The biggest and the most important takeaway from here is that correlation does not imply causation. So for example, if some random study found a massive correlation between divorce rates and margarine consumption, should we conclude that consuming margarine causes divorce? No, like that's a completely illogical conclusion. There are actually multiple non-causal explanations for an association. And the other thing to consider as well is if it was a really small sample size, like it might actually be like a fluke, which is actually one of the explanations we're going to look at as well. So the first one, common response, when two variables are strongly associated because they are both strongly associated with a third common lurking variable. So this is where general maths isn't black and white using formulas. It's actually, you've got to do like a bit of like thinking, which is why I find it quite interesting. So for example, scenario, if a study found a really strong association between like the number of scarves worn and the number of hot chocolates sold, does that mean the number of scarves worn and the number of hot chocolates sold are like directly correlated? Well, no, it actually doesn't. There could be a third like lurking common response variable, such as the temperature. So in this scenario, the temperature is associated with the number of scarves worn, and the temperature is associated with the number of hot chocolates being sold, because if it's colder, people will wear more scarves and buy more hot chocolates, which has made it seem like scarves and hot chocolates are correlated, but they're actually not. It's actually that lurking variable. Another one, confounding variables, where there are actually two possible causal explanations. An interesting example of this is crime and unemployment. When we look at like that, like sociologically, does crime drive people to unemployment, or does unemployment drive people to crime? Interesting. Which way does it go? How can we know? Another really interesting thing is when we're only doing like observational studies or correlational studies, when we're just like observing and collecting data, we can never actually talk about causation. We can only talk about correlation and association. To be able to talk about like causation, you have to conduct an experiment, which is where you like directly choose to manipulate a variable, which is something you might have looked at in science before. But we're only looking at association and correlation, so we can't be talking about causation. And like we touched on before, it could also just be a coincidence. Maybe their sample size was too small. Maybe the specific sample they looked at had this like correlation going on, but maybe it doesn't hold true for everywhere. Like it's just, sometimes it is actually just a coincidence.